When a sprinter hits top speed, their body is doing something very incredible. They're not accelerating, but they're also not slowing down. So what does the physics of such a moment look like? Okay, so here's a runner running at top speed. For elite sprinters, they mostly contact the floor straight downwards and right below the hip. So there would be a big force downwards. As the runner's foot strikes the ground, it also pulls back a little bit, causing a forward push. Since the runner we know is not accelerating, there must be a force counteracting this forward acceleration. And this is drag. So what exactly is drag? Drag is a resistive force. In this case, it's caused by air, which acts against the movement of an object. Let's say we have this ball and it's moving to the right. The drag would counteract this motion by pushing the ball to the left. What this also means is if the ball isn't moving, there's no drag. These resistive forces can be seen everywhere in our daily lives. This includes driving vehicles such as race cars and fighter jets, as well as physical activities such as skydiving and running. The formula for resistive forces is as follows. The force is equal to negative some constant b times v. What does this mean? It's actually pretty simple. The faster you're running, the more the air will push back against you, and this negative just indicates that it's going against your motion. And this constant b is different for every type of resistive force, but in this case, for running, we know that velocity squared is about proportional to the air resistance. If we graph out this relationship, we can see that the force increases very quickly as you run faster and faster. So why are resistive forces so important in running? Well, it helps explain why runners don't just keep accelerating, and rather they have to stop at a max velocity. This is because the drag keeps on increasing exponentially as they run faster, and their bodies are not able to produce enough force to counteract this drag to keep accelerating. Therefore, the runner's best bet is to maintain their posture and try to maintain the velocity rather than trying to increase it. Another reason we can't just keep on accelerating when we're sprinting is because of our biological limits. Even the most elite sprinters can only sprint all out for around 5 seconds, which is why they hit max velocity at around the 60-meter mark. Now that we know more about the forces going against our running, how about the forces that help us push forward? Here's the letter J, and it's an important concept to understand when we're understanding top speed mechanics. J represents the change in momentum, also known as impulse. And this may look complicated at first, but basically impulse is just the amount of force applied over some time interval. And I'm going to write it as from t0 to t1. So basically, in order for a runner to maintain max velocity, the impulse created by their foot strike must be equal to the change in momentum caused by drag. And this makes sense because the forward force has to equal to the reverse force in order to maintain the same velocity. And this is actually a lot more difficult than it may seem because most elite sprinters have a ground contact time of less than a tenth of a second, usually around 0.09. And you can only imagine how much force they have to apply during this small time interval in order to maintain their max velocity. So the next time you see a sprinter flying at top speed, remember, they're not just running. They're balancing forces, optimizing impulses, and living in the world of physics.